Welcome. Please prepare your environment for sleep. Lie down, relax your shoulders, and let the rhythmic cycle of industrial manufacturing guide you into a state of rest. Today's story is a deep dive into the thermodynamics of glass, structured specifically to quiet an overactive mind. Before you drift off, please hit the like button and subscribe to the channel to help others find this sleep aid. Sweet dreams. The industrial fabrication of a standard glass container begins not with the application of thermal energy, but with the rigorous chemical and mechanical preparation of raw mineral precursors. Glass, in its finished state, is defined as an amorphous solid, a material that possesses the structural density of a solid but retains the disordered molecular arrangement of a liquid. This unique physical state is achieved through the controlled cooling of a molten silicate mass, preventing the formation of a crystalline lattice. The primary constituent of this mass is silicon dioxide, or silica, which provides the fundamental structural framework of the glass. However, the high melting point of pure silica necessitates the introduction of specific fluxing agents and stabilizers to facilitate the manufacturing process at manageable industrial temperatures. The procurement and homogenization of these materials represent the foundational phase of the production cycle, occurring within a strictly regulated environment characterized by the continuous movement of bulk minerals and the steady operation of high-capacity filtration systems. The primary ingredient, silica sand, is sourced from high-purity quartz deposits where the concentration of silicon dioxide typically exceeds 99%. The extraction of this mineral involves the mechanical excavation of subterranean layers, followed by an extensive beneficiation process. This process is designed to remove undesirable impurities, particularly iron oxide, which would impart an unwanted green or amber tint to the finished glass. The sand is subjected to a series of washing cycles in large hydraulic classifiers, where high-velocity water jets strip away organic debris and fine clay particles. Subsequently, the sand is passed through magnetic separators of extreme intensity to extract any traces of ferromagnetic minerals. The resulting material is a collection of translucent subangular grains, each possessing a specific diameter and surface area. These grains are stored in massive, moisture-controlled silos, where the internal atmosphere is maintained to prevent the agglomeration of particles. To lower the transition temperature of the silica, a fluxing agent in the form of sodium carbonate, commonly referred to as soda ash, is introduced into the mixture. The chemical role of soda ash is to disrupt the strong silicon-oxygen bonds within the quartz structure, allowing the material to achieve a state of fluidity at significantly lower thermal thresholds. The procurement of soda ash involves the processing of trona ore or the utilization of the solvay process, resulting in a fine white crystalline powder. The physical consistency of the soda ash must be precisely matched to the grain size of the silica sand to prevent segregation during the subsequent mixing phases. The movement of this powder through the facility is managed by a network of enclosed pneumatic conveyors, which utilize pressurized air to transport the material from delivery bays to the primary storage units. The sound of this transport system is a persistent low-frequency hum that resonates through the steel ductwork of the batching plant. While soda ash facilitates melting, it also renders the resulting glass susceptible to water solubility. To ensure the chemical durability and structural integrity of the final container, a stabilizing agent is required. This is provided by calcium carbonate, sourced from naturally occurring limestone or dolomite deposits. The introduction of calcium ions into the silicate network provides the necessary resistance to chemical erosion, ensuring that the glass can safely contain aqueous solutions for extended periods. The limestone is processed through a series of primary and secondary crushers, reducing the large mineral blocks into a granular form that matches the specification of the silica and soda ash. This mechanical reduction is a high-energy process, occurring within heavy-duty machinery where the interaction between the stone and the hardened steel rollers produces a continuous grinding vibration. In addition to these primary minerals, the production of glass incorporates a significant proportion of cullet, which is recycled glass that has been crushed and sorted by color. The use of cullet is essential for the thermal efficiency of the furnace, as it requires less energy to remelt than the raw mineral batch. The integration of cullet also reduces the consumption of virgin raw materials and minimizes the carbon footprint of the manufacturing facility. The preparation of cullet involves the removal of metallic contaminants such as aluminum caps and ferrous rings, as well as the extraction of ceramic and stone fragments using advanced optical sorting technologies. These sorters utilize high-speed cameras and air jets to identify and eject non-glass particles from the moving stream of material. The sound of the cullet processing line is a sharp, irregular clattering of glass fragments as they move across vibrating screens and into the final blending hoppers. The final stage of the preparation phase is the systematic weighing and blending of the components into what is known as the batch. This operation is governed by a centralized control system that manages a series of precision load cells located beneath each raw material hopper. The system calculates the exact stoichiometric requirements for the specific glass formulation, accounting for the moisture content and chemical purity of each ingredient. The materials are dispensed in a predetermined sequence into a large-scale industrial mixer, where a set of rotating paddles facilitates the homogenization of the minerals. The goal of this mixing process is to create a perfectly uniform distribution of silica, soda ash, limestone, and cullet, ensuring that the chemical composition of the melt will be consistent throughout the furnace. Inside the mixer, the interaction of the various mineral grains creates a dense, abrasive environment. A small quantity of water is often added during the mixing cycle to minimize the generation of airborne dust and to prevent the segregation of the finer particles. The movement of the paddles through the heavy mineral mass produces a steady mechanical laboring sound, a rhythmic churning that signifies the transition from individual minerals to a unified batch. Once the mixing cycle is complete, the batch is transferred to a surge hopper, where it is held before being transported to the furnace charging system. The transport is typically handled by a series of covered belt conveyors, moving the gray granular mixture in a steady, unvarying stream towards the high-temperature environment of the melting chamber. The atmosphere of the batching plant is one of clinical industrial focus. The air is filtered to remove particulate matter, and the temperature is stabilized to maintain the flow characteristics of the powders. Every movement within the system is monitored by sensors that transmit data on flow rates, hopper levels, and motor temperatures to a central observation room. The logic of the system is absolute, functioning with a degree of mechanical regularity that ensures the continuity of the production line. The minerals, which existed for millions of years in a geological state, have now been systematically categorized, refined, and blended into a technical precursor for the vitrification process. At the conclusion of this chapter, the batch is positioned at the threshold of the furnace. It represents a state of potentiality, where the chemical identity of the glass has been established, but its physical form has yet to be realized. The transition from a granular solid to a molten liquid is the next mechanical event in the sequence, requiring the application of extreme thermal energy within a specialized refractory environment. The steady hum of the conveyors and the distant roar of the mixing paddles form the acoustic backdrop to this preparatory stage, a testament to the industrial scale and precision required to manufacture even the most common of objects. The process continues without interruption as the next sequence of weighing and blending begins, maintaining the constant flow of material that sustains the life of the furnace. The quality of the batch is verified by regular laboratory analysis, where samples are taken and subjected to X-ray fluorescence to confirm the elemental composition. Any deviation from the established formula is corrected in real time by adjusting the dispense rates of the individual hoppers. This constant feedback loop is essential for maintaining the optical clarity and mechanical strength of the glass. The movement of the batch towards the furnace is a slow, relentless progression, a river of mineral dust that serves as the bloodline of the glassworks. The state of readiness is now complete. The raw materials have been transformed into a technical substrate prepared for the intense thermal modifications that follow. The progression of the granular mineral batch from the mechanical hoppers into the thermal core of the glass furnace represents the critical transition from a heterogeneous solid mixture to a homogeneous liquid phase. This stage of the manufacturing cycle occurs within a massive, highly insulated structure known as a regenerative furnace, constructed from specialized refractory materials designed to withstand extreme thermal stress and chemical erosion. The furnace operates as a continuous flow system, maintaining a state of thermal equilibrium that is essential for the stability of the glass-forming reactions. The atmosphere surrounding the furnace is characterized by a profound radiant heat and a low-frequency atmospheric roar produced by the high-velocity combustion of natural gas and oxygen. The movement of the material into this environment is a slow, unvarying progression, managed by automated batch chargers that regulate the introduction of the minerals to match the rate of the liquid extraction at the terminal end of the system. The batch chargers, typically consisting of heavy-duty screw feeders or reciprocating blanket chargers, deposit the mineral mixture onto the surface of the molten glass already present within the furnace. As the gray granules encounter the incandescent surface, they form what are known as batch islands or logs, which float atop the dense liquid mass. The thermal energy required for the vitrification process is delivered through a series of massive burners located on the lateral walls of the furnace. These burners utilize a regenerative heat exchange system where the exhaust gases are routed through chambers filled with a lattice of refractory bricks. This lattice absorbs the residual heat from the departing gases, which is then transferred to the incoming combustion air during the subsequent cycle. This alternating movement of air and exhaust is a fundamental aspect of the furnace's energy management, occurring in rhythmic cycles that ensure the maximum efficiency of the thermal transfer. As the batch islands are propelled forward by the movement of the underlying melt, they undergo a sequence of complex chemical transformations. The initial reaction involves the decomposition of the sodium carbonate and calcium carbonate components. Under the influence of the intense heat, these minerals release carbon dioxide gas, which manifests as a violent bubbling within the transition zone. This release of gas is a vital part of the chemical integration, as the rising bubbles facilitate the mechanical mixing of the silica sand with the fluxing agents. The solid quartz grains begin to dissolve into the forming liquid, a process known as dissolution, where the strong molecular bonds of the silicon dioxide are broken by the presence of the sodium ions. This creates a primary silicate melt that is characterized by high viscosity and a dense population of microscopic gas inclusions. The internal architecture of the furnace is designed to manage the flow of this liquid through several distinct zones. The melting zone, or the melter, is where the bulk of the thermal energy is concentrated. Here, the temperature is maintained at levels where the viscosity of the glass is low enough to allow for rapid chemical fusion and the ascent of gas bubbles. The refractory blocks that line the melter are manufactured from high-density zircon, silica, alumina alloys, chosen for their ability to resist the corrosive action of the molten silicate. The interaction between the liquid glass and the refractory surface is a constant, slow process of surface attrition, monitored by a network of external cooling fans that maintain the structural integrity of the furnace walls. The movement of the glass within this zone is governed by natural convection currents, where the hotter material rises toward the center and the cooler material sinks along the perimeter, creating a continuous circulating flow that ensures the uniformity of the temperature distribution. Following the initial melting phase, the liquid glass enters the refining or fining zone. The primary objective of this stage is the removal of the gaseous inclusions that were generated during the decomposition of the carbonates. These bubbles, if not eliminated, would result in structural weaknesses and optical defects in the finished glass bottle. To facilitate the removal of these bubbles, fining agents such as sodium sulfate are included in the batch. At specific temperatures, these agents undergo a chemical reaction that produces a sudden expansion of gas, causing the small bubbles to coalesce into larger units. According to the laws of fluid dynamics, these larger bubbles possess a greater buoyancy and rise rapidly to the surface, where they escape into the furnace atmosphere. The surface of the glass in the fining zone is a spectacle of slow, deliberate activity as the liquid is purged of its internal irregularities. The homogenization of the melt is further enhanced by the use of mechanical stirrers or the introduction of compressed air through bubblers located at the bottom of the furnace. These systems create additional turbulence, ensuring that any localized variations in chemical composition or density are neutralized. The goal is to produce a glass mass that is perfectly consistent in its refractive index and thermal expansion characteristics. This state of homogeneity is essential for the subsequent forming operations, as any variation in the glass properties would lead to uneven wall thickness or spontaneous fracture during the cooling phase. The movement of the glass through the refining zone is a slow horizontal progression, moving toward a submerged passage known as the throat. The throat is a narrow, cooled opening that connects the main melting chamber to the working end of the furnace. As the glass passes through this passage, it undergoes a significant reduction in temperature, which increases its viscosity and prepares it for the conditioning phase. The throat also acts as a hydraulic barrier, preventing any unmelted batch fragments or surface scum from entering the refined glass stream. The transition through the throat is a moment of thermal stabilization where the turbulent energy of the melter is replaced by a more controlled laminar flow. Beyond the throat, the glass enters the distributor and the forehearths, a series of elongated refractory-lined channels that transport the liquid to the individual forming machines. The forehearths are equipped with their own heating and cooling systems, allowing for the precise calibration of the glass temperature. Each forehearth is divided into several thermal zones, where the temperature is adjusted in small incremental steps. This conditioning is necessary to ensure that the glass reaches the forming machine at the exact viscosity required for the specific bottle design. The atmosphere within the forehearths is one of quiet, intense heat, with the surface of the glass appearing as a smooth, glowing river of liquid light. The movement of the glass is slow and unvarying, guided by the gravity-fed slope of the channels. The sound in this area of the facility is a more localized hiss of the small burners and the steady whir of the cooling fans that manage the external skin temperature of the refractory housing. The entire melting and refining process is monitored by a centralized computer system that receives data from hundreds of sensors embedded within the furnace structure. These sensors measure the internal temperature of the melt, the pressure of the furnace atmosphere, the composition of the exhaust gases, and the level of the glass surface. Any deviation from the established parameters is corrected by the automated adjustment of the fuel-to-air ratio in the burners or the speed of the batch chargers. This constant monitoring ensures that the furnace remains in a state of stable operation for the duration of its campaign, which can last for years without interruption. The logic of the system is of absolute technical control, where the chaotic energy of the combustion and the chemical reactions are harnessed to produce a consistent, high-quality material. At the conclusion of this chapter, the glass has been transformed from a granular mixture of minerals into a refined, homogeneous, and thermally conditioned liquid. It is now positioned at the terminal end of the forehearth, ready to be divided into discrete units of volume for the molding process. The technical completion of the melting phase represents the transition from bulk material processing to individual unit fabrication. The steady, incandescent flow of the silicate mass continues, a river of potential forms moving toward the mechanical intervention of the forming machines. The environment of the glassworks remains characterized by the unyielding rhythm of the furnace, a constant backdrop to the intricate technical sequences that define the manufacture of the standard glass container. The transition of the molten silicate mass from the thermally regulated forehearth into the mechanical environment of the forming machine represents the first stage of individual unit fabrication. At the terminal end of the forehearth, the glass reaches the feeder mechanism, a complex assembly designed to convert a continuous flow of liquid into discrete, precisely measured portions of glass known as gobs. This process is governed by the synchronized movement of a refractory plunger and a set of mechanical shears. The plunger, a vertical cylinder manufactured from a high-density ceramic material, moves in a rhythmic, oscillating fashion within a specialized chamber called the spout. As the plunger descends, it forces a specific volume of glass through a circular aperture at the base of the spout, known as the orifice ring. The upward stroke of the plunger then creates a momentary vacuum that pulls the glass back, shaping the descending stream into an elongated cylindrical mass. The precise volume of each gob is critical, as any deviation in mass would result in a bottle with uneven wall thickness or insufficient capacity. This volume is controlled by the stroke length of the plunger and the diameter of the orifice ring, both of which are calibrated to account for the viscosity and surface tension of the melt. At the exact moment when the glass mass emerges from the orifice, a pair of high-speed mechanical shears intersects the stream. These shears are manufactured from specialized steel alloys and are continuously cooled and lubricated by a mist of water and oil to prevent the molten glass from adhering to the blades. The cutting action is a sharp, decisive event that separates the gob from the main body of the glass, allowing it to fall under the influence of gravity into the distribution system. The sound of the shearing cycle is a repetitive mechanical clicking that marks the pulse of the entire production line. Once separated, the incandescent gob enters a series of lubricated delivery chutes, collectively known as the gob distributor. This system utilizes a rotating or oscillating funnel to route the individual gobs to the various sections of the individual section or IS machine. The movement of the gob through the chutes is a rapid kinetic progression where the internal friction of the glass is minimized by a thin film of carbon-based lubricant. The geometry of the chutes is designed to maintain the orientation and temperature of the gob, ensuring that it reaches the forming mold with a consistent thermal profile. The atmosphere in this area is characterized by the persistent scent of vaporized lubricants and the rhythmic clatter of the gobs as they descend through the steel guides. The first stage of the molding process occurs within the blank mold, a heavy-duty casting manufactured from iron or specialized alloys. As the gob drops into the cavity of the blank mold, it is captured by a set of neck ring molds located at the base of the assembly. The neck ring is the first part of the container to be formed, as it defines the dimensions of the bottle's opening and the threads for the closure. This is achieved through a process known as the settle blow. Compressed air is introduced through a funnel at the top of the blank mold, forcing the molten glass downward into the neck ring assembly. This pressure ensures that the glass completely fills the intricate details of the finish, creating a solid structural foundation for the rest of the bottle. Following the formation of the neck ring, the funnel is removed and a baffle is placed over the top of the blank mold. A secondary air pressure, known as the counterblow, is then introduced from the bottom through a small opening in the plunger or the neck ring. This air forces the glass upward and outward against the walls of the blank mold, creating a hollow, thick-walled preform known as the parison. In some manufacturing configurations, particularly for wide-mouth containers, a mechanical plunger is used instead of air to press the glass into the mold, a method referred to as the press and blow process. Regardless of the method, the result is the same: a parison that possesses the final neck finish, but only a fraction of the ultimate body dimensions. The formation of the parison is a delicate balance of thermal management and mechanical timing. The internal surface of the blank mold is coated with a layer of graphite or specialized release agents to prevent sticking and to facilitate a smooth surface finish. As the glass touches the cooler metal of the mold, a thin, solidified skin forms on the exterior of the parison. This skin provides the structural integrity necessary for the parison to be moved, while the core remains molten and fluid. The duration of the contact between the glass and the mold, the dwell time, is measured in milliseconds and is strictly controlled to prevent excessive cooling, which would lead to surface defects or checks in the glass. The next mechanical event is the opening of the blank mold and the inversion of the parison. A set of mechanical arms governed by a complex system of gears and pneumatic cylinders grips the parison by the neck ring and rotates it through a 180-degree arc. This movement moves the parison from the blank side of the machine to the blow side. During this movement, the parison is suspended in the air, allowing it to stretch slightly under its own weight, a process known as reheat. The thermal energy from the interior of the parison migrates outward, softening the solidified skin and ensuring a uniform temperature distribution before the final blowing stage. The sound of the inversion is a powerful pneumatic hiss, followed by the mechanical thud of the arms reaching their terminal position. The parison is then enclosed within the final blow mold, which possesses the exact internal dimensions and aesthetic details of the finished bottle. The blow mold is often equipped with vacuum channels and cooling vents to assist in the expansion of the glass and to manage the temperature of the metal. The mechanical regularity of the IS machine is absolute, with each section operating in a staggered sequence to ensure a continuous output of product. The synchronization of the plungers, shears, distributors, and molds is managed by an electronic timing system that coordinates thousands of individual pneumatic and mechanical actions every minute. This logic ensures that the flow of glass is never interrupted and that each container is an exact duplicate of the one before it. The sound of the forming department is a dense industrial symphony, the roar of the cooling fans, the rhythmic pulses of the pneumatic valves, and the steady clatter of the delivery chutes. The environment is one of intense heat and mechanical complexity, where the molten silicate is systematically disciplined into its primary functional form. At the conclusion of this chapter, the parison is securely positioned within the blow mold, its internal temperature stabilized, and its surface prepared for the final expansion. The transition from a measured gob to a structured preform is complete, marking the midpoint of the container's physical realization. The logic of the manufacturing process continues to unfold as the parison awaits the final application of compressed air that will press it against the walls of the blow mold, establishing the final geometry of the standard glass bottle. The movement of the machinery is a relentless circular progression, a testament to the industrial efficiency that governs the production of vitreous containers. The transition from the parison stage to the final geometry of the glass bottle occurs within the meticulously controlled environment of the blow mold. This phase represents the terminal event in the shaping of the molten silicate, where the thick-walled preform is expanded to its ultimate dimensions through the application of internal pneumatic pressure. As the blow mold, a two-part assembly manufactured from high-grade cast iron or specialized copper-nickel alloys, closes around the suspended parison, a specialized interface known as the blowhead descends from its retracted position. The blowhead establishes a hermetic seal against the upper surface of the neck finish, ensuring that the subsequent introduction of compressed air is directed entirely into the internal cavity of the glass mass. The atmosphere within the forming section at this moment is a complex density of radiant heat, the sharp scent of vaporizing lubricants, and the rhythmic high-pressure pulse of the air valves. The final blow is a precision-timed pneumatic event. Compressed air, filtered and regulated to a specific pressure, is injected into the parison through the blowhead. Under the influence of this internal force, the molten glass, which still retains a high degree of plasticity at its core, expands outward at a rapid but controlled velocity. The glass wall fins as it stretches, moving toward the internal surfaces of the blow mold until it makes full contact with the metal. The pressure is maintained for a specific duration to ensure that the glass conforms to every detail of the mold's architecture, including the base contours, the shoulder curvature, and any embossed lettering or technical markings. This expansion is a display of fluid dynamics under constraint, where the surface tension of the glass is overcome by the pneumatic energy of the air supply. Simultaneously, the thermal energy of the glass is transferred to the cooler walls of the mold. This process of heat dissipation is critical for the structural stabilization of the container. If the glass were to remain in a liquid or semi-liquid state, it would collapse under its own mass once extracted. To manage this thermal exchange, the blow molds are equipped with a series of vertical or horizontal cooling channels through which ambient air is forced at high velocities. The temperature of the mold metal must be maintained within a narrow technical range. If the mold is too cold, the glass may develop surface fractures known as checks, while an excessively hot mold may cause the glass to adhere to the metal. The sound of this stage is dominated by the continuous high-frequency roar of the cooling fans and the intermittent heavy thuds of the blowheads as they cycle between their active and retracted states. In many modern configurations, the blowing process is assisted by a vacuum system integrated into the mold housing. This vacuum pulls the air out from the space between the parison and the mold wall, facilitating a more rapid and uniform expansion of the glass. This is particularly important for complex bottle designs where sharp corners or intricate surface textures are required. The synergy between the internal air pressure and the external vacuum ensures that the glass wall thickness remains consistent across the entire longitudinal profile of the bottle. The technical logic of the forming machine is a sequence of staggered operations, with each individual section performing these actions in a continuous overlapping loop that produces a constant stream of new containers. Once the glass has achieved sufficient structural rigidity, a state reached when the surface temperature drops below the glass transition point, the blowhead is retracted and the blow mold halves are mechanically separated. The bottle, now a solidified but still incandescent object glowing with a deep orange hue, remains supported by the neck ring. The final mechanical intervention of the forming machine is the action of the takeout mechanism. This mechanism utilizes a pair of precision-machined tongs governed by a pneumatic cylinder or an electronic servo motor to grip the bottle by the reinforced neck finish. With a fluid, oscillating motion, the takeout tongs lift the bottle out of the mold area and move it through an arc of approximately 180 degrees. The bottle is then deposited onto a stationary cooling plate, commonly referred to as the dead plate. This plate is perforated with thousands of microscopic holes through which a continuous stream of cold air is forced upward. This localized airflow provides a final, rapid cooling of the bottle's base, ensuring that the bottom of the container is perfectly flat and capable of supporting the weight of the contents without deformation. The bottle remains on the dead plate for a duration determined by the cycle timing of the machine, a period of atmospheric stabilization where the internal thermal gradients of the glass begin to normalize. The sound of the takeout cycle is a repetitive series of pneumatic hisses and the soft metallic clink of the tongs as they engage and disengage with the glass. From the dead plate, the bottles are moved onto the primary machine conveyor by a device known as the pusher. The pusher utilizes a synchronized sweeping motion to shift the containers from their individual cooling positions into a single file on the moving conveyor belt. This belt is typically manufactured from heat-resistant stainless steel mesh or specialized synthetic slats designed to withstand the thermal impact of the hot glass. The movement of the pusher is a display of mechanical coordination, ensuring that the bottles are spaced at equal intervals to prevent contact between the units. At this stage, the glass is still at a temperature exceeding 500 degrees Celsius, and any direct contact between the bottles could result in surface abrasions or the fusion of the glass surfaces. As the line of bottles moves away from the forming machine, they often pass through a hot end coating hood. This module facilitates a process known as chemical vapor deposition, where a thin molecular layer of tin or titanium oxide is applied to the exterior surface of the hot glass. The coating material is delivered in the form of a vaporized chemical precursor, which reacts with the thermal energy of the glass surface to form a hard, transparent film. This film serves two critical functions. It increases the mechanical strength of the glass by filling microscopic surface imperfections, and it provides a foundation for the subsequent cold end coating that will allow the bottles to slide against one another without scratching. The atmosphere within the coating hood is characterized by a faint metallic scent and the steady flow of the carrier gases. The movement of the containers along the conveyor is a slow, unvarying progression toward the next department of the facility. The bottles, while physically complete in their geometry, still possess significant internal stresses caused by the rapid cooling in the mold. These stresses must be relieved through a process of controlled reheating and slow cooling, a sequence that takes place in a long tunnel-like furnace known as a lehr. The transition from the forming machine to the lehr is the final stage of the hot end operations, where the liquid silicate has been successfully disciplined into a solid, functional container. The environment of the plant at this juncture is a symphony of industrial efficiency, where the constant production of new units is matched by the steady, linear movement of the existing stock. The logic of the manufacturing cycle is absolute. For every bottle that moves onto the conveyor, A new gob is being sheared at the feeder, and a new parison is being formed in the blank mold. The continuity of the process is a testament to the industrial engineering that governs the glassworks, where the chaotic energy of molten matter is transformed into the rigid, predictable forms of commerce. The bottles, now marching in a disciplined row, represent the successful application of pneumatic force and thermal management. They are no longer a liquid mass, they are individual units of production, ready for the final chemical and thermal treatments that will ensure their durability in the global marketplace. The steady hum of the conveyor and the distant roar of the furnace remain the constant, unvarying soundtrack of this mechanical evolution. The movement of the incandescent glass containers from the high-velocity forming environment into the linear thermal chamber known as the annealing layer represents a transition from mechanical shaping to molecular stabilization. As the bottles emerge from the forming machine and progress along the stainless steel conveyor, they possess significant internal structural stresses. These stresses are the direct result of the rapid and uneven cooling that occurred during the contact between the molten silicate and the metallic surfaces of the molds. If left unaddressed, these localized tensions within the glass matrix would render the containers extremely fragile, leading to spontaneous fracture during subsequent handling or thermal shocks. The objective of the annealing process is to relieve these permanent stresses by reheating the glass to a specific temperature and then cooling it in a slow, controlled manner that allows the molecular network to achieve a state of equilibrium. The entry point of the annealing layer is characterized by the presence of a lehr loader, a mechanical system that utilizes a synchronized transverse arm to push the single file line of bottles onto the wide moving belt of the furnace. This belt, manufactured from a heat-resistant stainless steel mesh, moves at a constant and exceptionally slow velocity, allowing for a high-density arrangement of containers. The bottles are organized into closely packed rows, creating a continuous field of glass that moves as a singular mass through the tunnel. The atmosphere at the entrance of the layer is characterized by a significant radiant heat and the steady mechanical clicking of the loader arm as it cycles between the conveyor and the layer belt. The sound of thousands of bottles moving in unison creates a low-frequency metallic rustle that permeates the local environment. The layer itself is a long, enclosed structure divided into several distinct thermal zones, each governed by its own set of burners and recirculating fans. The first section is the heating zone, where the bottles are exposed to intense infrared energy to raise their surface temperature back to the annealing point. This temperature, which typically sits just below the glass transition threshold, is the point at which the silicate molecules possess enough kinetic energy to move and rearrange themselves, thereby neutralizing the internal tensions without causing the container to lose its structural geometry. The heating is achieved through a series of gas-fired burners or electrical elements located both above and below the mesh belt, ensuring a uniform application of thermal energy across the entire longitudinal profile of each bottle. The physics of annealing involve the management of the thermal gradient within the glass wall. During the rapid cooling of the forming process, the exterior surfaces of the bottle solidify more quickly than the interior core, creating a state of compression on the outside and tension on the inside. By holding the glass at the annealing temperature, a phase known as the soak, the mechanical properties of the material become uniform. The duration of this soak is calculated based on the wall thickness and the specific chemical composition of the glass melt. Inside the heating zone, the air is continuously recirculated by high-capacity centrifugal fans, creating a laminar flow that prevents the formation of localized hotspots or cold pockets. The sound within this section of the layer is a steady, hollow roar produced by the movement of heated air through the insulated ductwork. Following the soaking phase, the bottles progress into the controlled cooling zones. This is the most critical part of the annealing cycle, as the temperature must be reduced at a rate that is slow enough to prevent the reintroduction of thermal stresses. The glass passes through the strain point, the temperature below which the material becomes a rigid solid and the molecular structure is permanently locked into place. The cooling rate is managed by adjusting the ratio of ambient air introduced into the tunnel and the volume of heated air being recirculated. This transition is a slow, unvarying progression through several dozen meters of the insulated tunnel, where the radiant orange glow of the glass gradually fades until the containers appear transparent once again. The structural integrity of the silicate network is monitored throughout this process by a series of thermocouple sensors embedded in the walls and the floor of the lair. These sensors transmit real-time data to a centralized control system, which modulates the burner intensity and fan speed to maintain the preset annealing curve. The logic of the system is one of absolute consistency, ensuring that every container, regardless of its position on the wide belt, receives the exact same thermal treatment. The environment inside the lair is one of sterile industrial focus, where the chaotic energy of the forming stage is systematically disciplined into a state of permanent stability. The movement of the belt is so slow that it is almost imperceptible to the casual observer, yet it represents the heartbeat of the cold end operations. As the containers approach the terminal end of the lair, they enter the final cooling stage, where high-velocity ambient air is forced over the glass to reduce its temperature to a level suitable for manual or mechanical handling. By the time the bottles emerge from the lair, their temperature has been reduced from nearly 600 degrees to approximately 60 degrees Celsius. The emergence from the lair is a transition from the intense and closed heat of the tunnel to the cooler, more open atmosphere of the inspection department. The bottles, now structurally sound and stress-free, represent a successful application of thermodynamic principles. They are no longer a fragile assembly of competing tensions. They are durable, functional units of storage. At the exit of the lair, the bottles are subjected to a cold end coating process. This involves the application of a thin protective layer of lubricant, typically a polyethylene-based emulsion or a similar chemical compound. This coating is delivered through a series of spray nozzles located both above and below the conveyor belt. The primary purpose of the cold end coating is to reduce the coefficient of friction on the exterior surface of the glass. This ensures that when the bottles move at high speeds through the subsequent inspection and packaging lines, they can slide against one another without causing surface scratches or abrasions. These microscopic scratches, if not prevented, could act as stress concentrators and lead to the failure of the container during the filling process. The sound of the coating station is a continuous, fine hiss of the pressurized spray, accompanied by a faint waxy aroma. The movement of the bottles away from the lair is managed by a single liner mechanism, which utilizes a series of converging guides and moving belts to reorganize the wide mass of glass back into a single file line. This reorganization is a rhythmic mechanical process where the bottles are gently funneled toward the inspection modules. The acoustic signature of this area is a dense metallic clinking as the containers make contact with one another and the stainless steel guides. The logic of the production line remains one of constant, unvarying flow, with the output of the lair perfectly matched to the throughput of the forming machines. For every row of bottles that enters the lair, a row of cooled, coated containers emerges at the other end, ready for the final verification of their quality. The state of the glass at the conclusion of this chapter is one of chemical and physical readiness. The raw minerals that were melted in the furnace and shaped in the molds have now been permanently stabilized within the annealing layer. The internal architecture of the silicate matrix has achieved its final configuration, providing the container with its characteristic clarity and strength. The bottles continue their journey along the conveyor, moving toward the automated inspection systems that will verify their dimensional accuracy and structural integrity. The steady hum of the facility remains an unyielding backdrop to this industrial evolution, a testament to the complex technical sequences required to transform a simple mixture of sand and soda into a standardized glass container. The emergence of the annealed glass containers from the stabilized environment of the lehr marks the beginning of the cold end inspection phase, a sequence characterized by the relentless application of optoelectronic and mechanical scrutiny. As the bottles move along the high-speed conveyor belts, they are no longer viewed as a continuous mass of material, but as individual units of production that must adhere to a strict set of dimensional and structural specifications. The objective of this department is the total elimination of any unit that possesses even a microscopic deviation from the established technical standard. This process is governed by a series of integrated inspection modules, each designed to detect specific categories of defects through the use of high-resolution imaging, laser triangulation, and mechanical pressure testing. The atmosphere of the cold end is defined by the high-frequency hum of electronic processors, the rapid-fire strobe of inspection lights, and the persistent metallic clinking of the containers as they are diverted through the various scanning stations. The first stage of the inspection sequence often involves the verification of dimensional accuracy. The bottles pass through a module equipped with mechanical gauges or non-contact laser sensors that measure the total height, the verticality of the body, and the external diameter of the container at multiple points. Any bottle that deviates from the predetermined tolerances, even by a fraction of a millimeter, is immediately identified for rejection. Simultaneously, the finish of the bottle, which includes the threads and the sealing surface of the neck, is subjected to a rigorous examination. A specialized sensor, often employing a capacitive or optical measurement technique, checks for choked bores or overpress finishes, ensuring that the closure will fit perfectly and maintain a hermetic seal during the subsequent filling process. Following the dimensional check, the containers enter the optoelectronic sidewall inspection station. This module is the most complex part of the verification process, utilizing a series of high-speed cameras and specialized backlighting to examine the entire transparency of the glass matrix. As each bottle rotates or passes through the scanning field, the cameras capture thousands of frames per second, which are processed in real time by a central logic unit. The system is programmed to identify vitreous anomalies, such as stones, which are small fragments of unmelted refractory material, or seeds, which are microscopic gas bubbles that escaped the fining process in the furnace. The logic of the image processor is designed to distinguish between harmless surface variations and structural defects that could compromise the integrity of the bottle under pressure. A critical part of this optical scrutiny is the detection of checks, microscopic fractures that can occur during the forming or cooling stages. These checks are often invisible to the naked eye, but can lead to catastrophic failure when the bottle is carbonated or subjected to thermal shock. To identify these defects, the inspection module utilizes high-intensity light sources positioned at specific angles. If a fracture is present, the light reflects off the internal surface of the crack, creating a glint that is detected by the optical sensors. The sound in this area of the facility is a rhythmic electronic chirping as the system confirms the passage of each successful unit and marks the coordinates of those destined for rejection. Beyond optical and dimensional checks, the structural durability of the glass is verified through mechanical stress testing. One such test is the squeeze tester, where the bottle is passed through a series of rotating discs or belts that apply a calibrated external pressure to the sidewalls. This test is designed to simulate the stresses the container will encounter during the automated filling and labeling processes in a commercial bottling plant. Any unit with an internal structural weakness, such as an area of excessively thin wall thickness, will fail under this pressure and be removed from the line. The movement of the bottles through the squeeze tester is a continuous fluid progression, where the mechanical resistance of the glass is the primary variable being monitored. To further ensure the consistency of the glass distribution, the bottles are passed through a wall thickness measurement system. This module typically utilizes a series of sensors that employ electromagnetic or ultrasonic principles to measure the exact thickness of the glass at various heights and orientations. The system calculates the ratio between the thinnest and thickest parts of the bottle, ensuring that the distribution of the silicate mass is uniform. This is essential for the thermal stability of the container, as uneven glass distribution can lead to localized stress concentrations during rapid temperature changes. The data from these measurements is transmitted back to the hot end of the facility, where it is used to fine-tune the timing of the forming machines and the distribution of the gobs. The final stage of the inspection sequence is the verification of the base of the bottle. The containers are lifted or tilted to allow cameras to inspect the bottom surface for any irregularities, such as leers or uneven cooling marks that could prevent the bottle from standing vertically. At the same time, the mold numbers and tracking codes embossed on the glass are scanned to maintain a complete history of each unit's production. This allows the facility to trace any recurring defects back to a specific section of the forming machine or a specific cavity in the mold. The logic of the inspection system is a closed feedback loop, constantly refining the production parameters to minimize waste and maximize the output of high-quality glass. Any bottle that fails to meet the criteria of any of these inspection modules is directed toward a rejection gate. This mechanism utilizes a high-velocity burst of compressed air or a mechanical pusher to divert the defective unit onto a separate conveyor belt. These rejected bottles are then transported to a crusher where they are converted back into cullet, raw glass fragments that will be returned to the furnace to be melted and formed again. This cyclical nature of the production process ensures that no material is wasted, even as the inspection standards remain uncompromisingly high. The sound of the rejection gate is a sharp, intermittent hiss of air, followed by the distant clatter of glass fragments falling into a collection bin. The movement of the successful bottles continue along the single-file conveyor, moving away from the strobe lights and sensors of the inspection department. The bottles, now verified as structurally sound and dimensionally perfect, represent the successful application of industrial automation and optoelectronic precision. They have survived the intense heat of the furnace, the mechanical violence of the forming machine, the thermal discipline of the lehr, and the exhaustive scrutiny of the cold end sensors. They are no longer just products of a factory, they are calibrated technical instruments designed for the safe and efficient storage of liquids. The environment of the facility at this stage is one of calculated efficiency. For every bottle that reaches the end of the inspection line, thousands of others are at various stages of the production cycle, from the raw materials in the silos to the molten mass in the forehearth. The steady hum of the electronics and the rhythmic movement of the conveyors form the acoustic signature of this terminal phase. The containers now proceed toward the final department of the glassworks, where they will be organized, palletized, and prepared for their journey into the global supply chain. The logic of the process remains unyielding, a testament to the complex technical sequences required to ensure that a simple glass bottle is a masterpiece of industrial consistency. The transition of the inspected glass containers from the single-file conveyor system into the final stages of accumulation and packaging represents the terminal phase of the production sequence within the glassworks. At this juncture, the individual identity of each bottle is subsumed into a larger collective unit, organized according to a strict geometrical matrix designed for maximum stability during global transit. As the containers leave the optoelectronic scanning modules, they move toward a high-capacity accumulation table, also known as a bidirectional mass flow conveyor. This system utilizes a wide, low-friction belt that allows the single stream of bottles to expand into a dense, multi-row configuration. The movement is governed by a series of diverging guides and oscillating diverter arms that ensure a constant flow without causing excessive surface pressure between the containers. The atmosphere in this terminal zone is defined by a continuous rhythmic metallic rustle, a sound produced by the contact of thousands of glass surfaces moving in a state of laminar confluence. The logic of the accumulation table is to act as a hydraulic buffer, absorbing the output of the high-speed forming machines and preparing the units for the discrete movements of the palletizing system. The bottles are systematically funneled toward the layer forming section, where a set of pneumatic pushers or mechanical sweeping arms organizes the glass into a precise rectangular grid. Every row and every column within this grid is calculated to maximize the spatial efficiency of the standard pallet dimensions. This organizational process is a display of repetitive mechanical precision, where the movement of the sweeping arm is synchronized with the advancement of the conveyor belt. The sound of the layer forming station is a steady cycle of pneumatic hisses, followed by the muffled clatter of the glass as it is nudged into its final coordinates. Once a complete layer of bottles has been collated, the automated palletizer initiates its primary mechanical cycle. This machine utilizes a massive 4-axis overhead gantry or a specialized lifting head equipped with a vacuum-assisted surface plate. The lifting head descends with a low-frequency hum, landing gently upon the tops of the containers. A series of flexible suction bellows or mechanical side grippers engage with the bottles, securing the entire layer consisting of several hundred units within a singular grip. The gantry then lifts the layer and moves it horizontally toward the waiting pallet. The movement is fluid and unvarying, controlled by advanced servo motors that ensure a soft landing to prevent any impact-related structural damage to the annealed glass. The foundation of this organized mass is the standard industrial pallet, typically manufactured from heat-treated timber or reinforced high-density polyethylene. The pallet is positioned within a central elevator system that adjusts its vertical height after each subsequent layer is deposited. To maintain the structural integrity of the growing stack and to prevent direct glass-to-glass contact between the layers, an automated insertion mechanism places a tier sheet, a flat sheet of corrugated cardboard or specialized plastic, on top of each completed layer. These tier sheets act as a frictional stabilizer and a protective barrier, distributing the vertical load evenly across the entire surface area of the pallet. The sound of the palletizer is a complex mechanical symphony of whirring motors, the rhythmic thud of the tier sheet feeder, and the persistent hiss of the vacuum pumps. As the stack reaches its final height, often consisting of 6 or 7 individual layers of glass, the completed pallet is transferred from the elevator onto a heavy-duty roller conveyor. This conveyor transports the unstable stack toward the rotary stretch wrapper module. At this stage, the bottles are held together only by the weight of the glass and the friction of the tier sheets. They are highly susceptible to shifting or toppling. The stretch wrapper is a specialized machine that utilizes a rotating arm or a revolving turntable to apply multiple layers of low-density polyethylene film around the exterior of the pallet. The film is dispensed from a tensioned roll and is pre-stretched to its elastic limit before application, ensuring a high degree of centripetal force that binds the glass units into a single, rigid, monolithic block. The application of the stretch wrap is a hypnotic circular progression. The film dispenser moves vertically along the height of the pallet as it rotates, creating a spiral pattern that overlaps with each revolution. The sound of the wrapping process is a persistent, high-pitched whine as the plastic film is pulled through the tensioning rollers, accompanied by the low rumble of the rotating turntable. This encapsulation provides more than just structural stability. It also creates a hermetic barrier that protects the sterile interiors of the bottles from atmospheric dust, moisture, and potential contaminants during the logistics cycle. The final revolution of the wrapper involves a top cap application, where a separate sheet of plastic is draped over the final layer before the final film layers are applied, ensuring the pallet is fully enclosed on all 6 sides. Following the encapsulation, the pallet moves to the automated labeling station. Here, a thermal transfer printer generates a logistical tracking label containing a unique identification code, the date of manufacture, the mold cavity numbers, and the destination coordinates. A pneumatic applicator arm presses the adhesive label onto the exterior of the stretch wrap. This label serves as the digital link between the physical object and the global supply chain management system, allowing the facility to track the performance of the glass across its entire life cycle. The movement of the labeled pallet continues toward the terminal end of the conveyor line, where it is finally removed by a high-capacity forklift or an automated guided vehicle, or AGV. The warehouse environment is a vast, climate-controlled space where thousands of pallets are stored in high-density racking systems. The atmosphere is one of profound stillness, contrasting with the intense heat and mechanical violence of the hot end of the factory. The pallets are organized according to a strict logistical logic, awaiting the arrival of intermodal shipping containers or heavy-duty transport vehicles. The transition from the factory floor to the warehouse represents the completion of the industrial cycle. The raw minerals that began as sand, soda, and lime have been systematically transformed into thousands of identical, high-quality technical instruments, now securely bound and ready for their functional life in the marketplace. The movement of the glass from the warehouse into the global transit network is the final mechanical event in this history. Whether transported by rail, sea, or road, the containers are subjected to a continuous series of low-frequency vibrations and gravitational forces, all of which are successfully resisted by the structural integrity of the annealed glass and the tension of the stretch wrap. The bottles, once a chaotic molten liquid at temperatures exceeding 1,000 degrees, are now silent, cold, and stable. They represent a successful triumph of thermodynamic and mechanical engineering, a standardized solution for the storage and preservation of liquids, manufactured with a degree of consistency that ensures their reliability across billions of individual units. As the heavy doors of the shipping container are closed and the logistical journey begins, the factory continues its unvarying rhythm. At the other end of the facility, new minerals are being weighed, a new batch is being blended, and a new river of molten silicate is flowing toward the furnace throat. The cycle is absolute and perpetual, a testament to the industrial logic that sustains the modern world. The steady hum of the facility, the distant roar of the burners, and the rhythmic clicking of the conveyors remain the constant acoustic backdrop to this ongoing evolution of matter. The story of the standard glass bottle is one of relentless precision, a technical odyssey that concludes in the silent, dark interior of a moving container, traveling towards its destination in the global web of commerce. The movement of the palletized glass containers from the stabilized environment of the warehouse into the high vibration domain of intermodal transit represents a shift from static storage to kinetic endurance. Once the pallets are loaded into the dark rectangular confines of a shipping container or a heavy-duty trailer, they are no longer subject to the controlled atmosphere of the factory. Instead, they become passive participants in a global logistical network characterized by a continuous spectrum of mechanical frequencies and gravitational shifts. The transition into the transit phase is a process of physical insulation, where the structural integrity of the individual bottle and the collective tension of the stretch wrap film are tested against the realities of long-distance transport. The interior of the shipping container is a space of profound sensory isolation, yet it is filled with a constant low-frequency resonance produced by the interaction between the vehicle's suspension system and the irregularities of the road or rail surface. The physics of this transit phase are governed by the principles of vibrational dampening and load distribution. Each pallet, weighing approximately 1,000 kilograms, exerts a significant vertical force on the wooden slats of its base. As the vehicle moves, the glass containers experience a series of rhythmic oscillations that are transmitted through the pallet and the tier sheets. The presence of the cold end polyethylene coating applied at the terminal end of the lehr becomes critical here. This molecular layer allows the bottles to vibrate against one another with a minimal coefficient of friction, preventing the formation of surface abrasions or the accumulation of static electricity. The logic of the packaging system ensures that the energy of the transit is dissipated across the entire monolithic block of the pallet, rather than being concentrated on a single fragile point. Upon arrival at the destination, a high-capacity automated bottling facility, the pallets are extracted from the transport vehicle by a sequence of synchronized forklifts or automated guided vehicles. This marks the beginning of the technical re-entry phase, where the organized mass of glass is systematically deconstructed into its constituent units. The depalletizing process is the mechanical inverse of the palletizing stage described in the previous chapter. The pallet is positioned within a heavy-duty elevator system that gradually raises the stack one layer at a time to the level of the primary intake conveyor. A high-speed sweep-off arm, governed by a series of pneumatic sensors and proximity switches, gently slides the entire layer of bottles onto a broad accumulation table. The removal of the tier sheet is handled by a secondary vacuum-assisted arm, which deposits the used cardboard into a recycling hopper with a soft, repetitive thud. The atmosphere of the intake department is characterized by a dense metallic clatter, a sound produced by the sudden liberation of hundreds of bottles from their compressed state. As the bottles spread out across the accumulation table, they transition from a static grid into a fluid, multi-row stream. This is a process of hydraulic-like confluence, where the containers are funneled through a series of converging stainless steel guides. The goal of this stage is to reorganize the glass into a single file line that can be processed by the high-velocity filling equipment. The movement is managed by a series of variable speed belts that utilize low-friction synthetic materials to prevent surface damage. The sound of this reorganization is a continuous high-pitched ringing as the bottles collide gently with one another and the metallic side rails of the conveyor system. Before the glass can be introduced to the liquid product, it must undergo a rigorous process of internal and external sterilization. The bottles enter a tunnel-like machine known as a rotary rinser or an air jet cleaner. In this module, each bottle is gripped by a set of specialized rubber-coated clamps and inverted through a 180-degree arc, positioning the opening directly over a series of high-pressure nozzles. A burst of ionized air or demineralized water is injected into the internal cavity of the bottle, dislodging any microscopic particles of dust or fiber that may have accumulated during transit. The duration of this rinse is measured in milliseconds, yet it is sufficient to ensure that the interior surface of the silicate matrix is chemically and physically inert. The sound of the rinser is a rhythmic, percussive series of air blasts, followed by the mechanical clicking of the clamps as they release the bottles back onto the line. The sterilized bottles then progress through a secondary inspection module, which serves as a final verification of their structural integrity after the rigors of transport. This system, similar to the cold-end inspection at the glassworks, utilizes high-speed cameras and laser sensors to check for any fractures or checks that may have developed during the vibrational cycles of the journey. The system also verifies the orientation of each bottle, ensuring that the finish is perfectly aligned for the filling valves. The logic of this inspection is an uncompromising safeguard designed to prevent the catastrophic failure of a container when it is subjected to the high-pressure environment of the filling bowl. Any unit that fails this final check is immediately diverted into a cullet collection bin, where it will eventually return to the furnace as raw material. The conveyor line at this stage is a display of extreme linear velocity. The bottles move at a rate of several hundred units per minute, appearing as a blurred, translucent ribbon of light. To manage this speed, the facility utilizes a centralized control system that modulates the flow of bottles to prevent back pressure, a condition where the bottles push against one another with enough force to cause a blockage or a break. The movement is governed by a series of electronic cams that synchronize the speed of the rinser, the filler, and the capper. This synchronization is essential for maintaining the laminar flow of the glass, ensuring that each container enters the next stage of the process at the exact microsecond required by the mechanical timing of the system. The environment of the bottling plant is one of clinical precision and immense industrial scale. The air is filtered to a pharmaceutical standard, and the temperature is stabilized to prevent any thermal shock to the glass. The acoustic signature of the facility is a complex layering of sounds: the high-frequency whine of the high-speed belts, the rhythmic pulses of the pneumatic valves, and the deep atmospheric hum of the massive liquid pumps. Within this environment, the glass bottle is no longer an object of manufacturing. It has become a technical vessel, a sterile and calibrated container ready to fulfill its primary function. The journey from the raw minerals in the furnace to this moment of readiness has been a technical odyssey of thermodynamic and mechanical engineering. As the bottles leave the sterilization module and move toward the filling bowl, they enter a state of maximum potentiality. The interior of each container is a vacuum-cleaned, sterile void, prepared to receive its precisely measured volume of liquid. The movement of the glass is relentless and unvarying, a testament to the industrial logic that sustains the modern supply chain. The factory remains a world of constant motion, where the individual unit is merely a single point in a perpetual stream of production. The steady clinking of the glass and the rhythmic movement of the machinery form the soundtrack to this terminal phase of preparation, a sound that has become the pulse of global commerce. The state of the glass at the conclusion of this chapter is one of absolute readiness. The bottle has survived the intense heat of its creation, the discipline of the annealing lehr, the scrutiny of the inspection sensors, and the kinetic stresses of global transit. It has been washed, dried, and verified for the final time. It stands now at the threshold of the filling machine, where it will finally lose its hollow identity and become a finished consumer product. The story of the glass bottle continues, moving from the domain of manufacturing into the domain of consumption, yet the underlying technical principles remain the same: the management of matter through the application of precise mechanical and thermodynamic force. The progression of the sterilized glass bottle into the heart of the filling department represents the moment of functional transition, where the hollow silicate form is integrated with its intended liquid content. This stage occurs within a high-speed rotary filling machine, a massive stainless steel carousel that governs the movement of hundreds of containers per minute. The process is defined by the principles of isobaric pressure equalization, a method designed to facilitate the rapid transfer of liquid while preventing the loss of carbonation or the introduction of excessive oxygen. As each bottle enters the filling carousel, it is captured by a set of centering bells that align the neck finish precisely with the filling valve. The atmosphere in this section is characterized by a dense, rhythmic hissing of pressurized gases and the constant cascading sound of water used for external lubrication and temperature control. The filling cycle begins with the establishment of a hermetic seal between the valve and the bottle finish. Once the seal is confirmed by a pneumatic sensor, the valve initiates the pre-evacuation phase. A vacuum pump extracts the ambient air from within the bottle, replacing it with a controlled atmosphere of carbon dioxide or nitrogen. This displacement is essential for the preservation of the liquid's chemical stability, as any residual oxygen would lead to oxidative degradation over time. Following the pre-evacuation, the valve opens the gas path to equalize the internal pressure of the bottle with the pressure within the main product reservoir, known as the filling bowl. Only when this state of isobaric equilibrium is achieved can the liquid flow begin, moving under the influence of gravity and a slight pressure differential into the glass cavity. The fluid dynamics of the filling process are a display of controlled laminar flow. The liquid is directed down the internal walls of the bottle by a specialized spreader, a conical or spherical component within the valve, which ensures that the fluid moves in a thin film rather than a turbulent stream. This minimizes the formation of foam and ensures a consistent fill level across the entire production run. The displaced gas within the bottle is returned to the filling bowl through a central vent tube, maintaining the pressure balance of the entire system. The logic of the filling machine is an unyielding sequence of mechanical events, where the duration of each phase is measured in milliseconds and governed by the rotational velocity of the carousel. The sound of this area is a persistent mechanical thrumming, punctuated by the sharp pulses of the vent valves as they cycle through their operations. As the liquid reaches the predetermined fill height, the vent tube is submerged, effectively closing the gas return path and stopping the flow of the product. The filling valve then enters the snifting or depressurization phase. This involves the gradual release of the internal pressure back to atmospheric levels, a process that must be executed with extreme precision to prevent the sudden expansion of gas and the subsequent eruption of the liquid from the bottle. This gradual release is achieved through a series of microvalves that modulate the exhaust flow, creating a characteristic fading hiss that signifies the conclusion of the filling event. The bottle, now containing its precisely measured volume of product, remains supported by the carousel until it is transferred to the neighboring capping module. The capping process represents the final mechanical intervention that ensures the long-term integrity of the container. For a standard glass bottle, this typically involves the application of a crown cork or a specialized aluminum screw cap. The containers move along a short, synchronized star wheel into the capper, where a set of rotating heads, each equipped with a precision machined chuck, awaits them. For a crown cork, the capping head utilizes a vertical downward force to crimp the metallic skirt of the cap around the reinforced flange of the neck finish. This action compresses a synthetic liner, often a specialized polymer or a natural cork composite, against the glass surface, creating a permanent gas-tight seal. The force required for this crimping is several hundred kilograms, yet it is applied with a degree of mechanical softness that prevents the fracture of the annealed glass. The logic of the capping machine is one of absolute torque and pressure control. Every capping head is equipped with an electronic or magnetic clutch that limits the rotational and vertical force to within a narrow technical range. This ensures that every seal is uniform, preventing the leaks that would occur from under-tightening or the glass damage that would result from over-compression. The movement of the capping heads is a rapid vertical oscillation synchronized with the movement of the bottles through the star wheel. The acoustic signature of the capping station is a rhythmic mechanical thumping, the sound of the caps being fed from a vibrating hopper through a series of steel chutes and into the capping heads. Once sealed, The bottles are moved through an external rinsing module to remove any traces of liquid that may have spilled during the filling process. This is followed by a visual inspection system, often employing a high-intensity laser or a gamma-ray sensor to verify the final fill level and the correct placement of the cap. Any bottle that does not meet the specified fill height or possesses a misaligned closure is immediately diverted into a rejection lane. The bottles that pass this final verification then progress toward the labeling department. The labeling process is a high-speed application of identity. The bottles enter a rotary labeling machine where they are positioned on a set of rotating pedestals. As each bottle spins, a set of vacuum-assisted pallets applies a thin layer of cold glue or pressure-sensitive adhesive to a paper or plastic label. The label is then transferred onto the glass surface, where a series of brushes and foam rollers smooth it into place, ensuring that there are no wrinkles or air bubbles trapped beneath the material. The speed of the labeler is often the highest of any machine in the facility, with the bottles appearing as a continuous vibrating blur of color and light. The sound of the labeling station is a rapid-fire clicking of the glue pallets and the soft, repetitive whir of the rollers as they interface with the moving glass. The movement of the labeled and sealed bottles away from the filling department is a slow, orderly progression toward the final packaging area. The bottles, once a collection of raw minerals and then a hollow silicate form, have now achieved their final configuration as a finished consumer product. They represent a successful convergence of chemical engineering, fluid dynamics, and mechanical precision. The atmosphere of the bottling plant at this terminal stage is one of industrial fulfillment. For every bottle that leaves the labeling machine, thousands of others are behind it, moving through the same exhaustive sequence of sterilization, filling, and sealing. The steady hum of the facility and the rhythmic movement of the conveyors form the unvarying soundtrack to this terminal phase of production. The state of the glass at the conclusion of this chapter is one of functional completion. The bottle has been filled, sealed, and labeled. It is now a durable, hermetic vessel, capable of preserving its contents for months or years in the global marketplace. The journey of the glass is almost at its end, moving away from the machines of its creation and toward the hands of the consumer. The story of the standard glass bottle is a testament to the complex technical systems that govern the modern world. A journey that began in the intense heat of a furnace and ends in the cold, disciplined efficiency of an automated bottling line. The final phase of the glass container's industrial journey begins with its departure from the labeling module and its entry into the secondary packaging department. Here, the individual bottles, now sealed and identified, are organized into larger collective units for efficient distribution. This process occurs within a high-speed case packer, a machine that utilizes a complex system of dividers and mechanical grippers to group the bottles into a predetermined matrix, such as a 4x6 or a 3x4 configuration. The bottles move along a low-friction conveyor guided by stainless steel rails that gradually converge to create the necessary row density. The sound of this area is a constant rhythmic clinking of glass against glass, overlaid by the deep, resonant thud of the case packer's overhead assembly as it cycles between the conveyor and the waiting shipping cartons. The secondary packaging material is typically corrugated fiberboard, a composite structure designed to provide high compressive strength and vibrational dampening. An automated case erector transforms flat cardboard blanks into three-dimensional boxes through a sequence of mechanical folds and the application of thermoset adhesive. As the box reaches the packing station, the gripper head, equipped with individual pneumatic suction cups or flexible rubber fingers, descends and captures a full group of bottles by their neck finishes. The bottles are lifted and lowered with a fluid vertical motion into the internal cells of the carton. This placement is executed with extreme precision to ensure that the glass walls do not impact the base of the carton with enough force to cause structural fatigue. The logic of the case packer is a synchronized loop of detection, acquisition, and deposition occurring at a rate of several dozen cases per minute. Once filled, the cartons progress to the case sealer, where the top flaps are folded and secured with adhesive or reinforced pressure-sensitive tape. This creates a self-contained, structurally rigid unit that protects the glass from external impact and atmospheric moisture. The sealed cases then move toward the secondary palletizing area, the final mechanical consolidation within the bottling facility. Similar to the process described at the glassworks, an automated palletizer organizes the cases into layers and stacks them upon a standard industrial pallet. However, because the containers are now filled with liquid, the total mass of the pallet is significantly higher, often exceeding 1,200 kilograms. The completed pallet is then subjected to a final stage of stretch wrapping, where a thick layer of polyethylene film binds the cases into a stable, monolithic block ready for the global supply chain. The distribution phase is a period of extended mechanical and thermal stability. The pallets are transported via heavy-duty vehicles or intermodal shipping containers to regional warehouses and eventually to retail environments. Throughout this transit, the glass remains chemically inert, maintaining the purity of the contents, regardless of external fluctuations in temperature or pressure. The sealed bottle sits on a retail shelf, a silent witness to the passage of time, where its transparency allows for the visual verification of the product's quality. The logic of the glass is its reliability, the assurance that the liquid remains exactly as it was at the moment of the isobaric filling cycle. The climax of the bottle's functional life occurs during the act of consumer opening. This is a moment of sudden thermodynamic and mechanical transition. As the consumer applies a lever force to the crown cork or a rotational torque to the screw cap, the hermetic seal is compromised. The internal pressure, which has been maintained in a state of equilibrium for months, is suddenly released into the atmosphere. This release produces a characteristic acoustic signature, a sharp, dissipating hiss as the compressed gases expand into the lower pressure environment. The physical failure of the seal allows for the first interaction between the internal liquid and the external atmosphere. The pour is a display of gravity-fed fluid dynamics, where the liquid moves over the smooth, non-porous surface of the glass finish, a surface that remains as clean and uncontaminated as it was on the day of its creation in the furnace. Once the contents have been consumed, the glass bottle transitions from a vessel of storage to a unit of post-consumer material. However, unlike many other packaging materials, the glass container possesses a unique capacity for total circularity. The empty bottle is collected and transported to a specialized recycling facility, where it begins its re-entry into the industrial cycle. The first stage of this process is the mechanical crushing of the glass into small fragments, known as cullet. This cullet is then subjected to a rigorous sequence of sorting operations. High-speed optical sorters utilize infrared sensors and air jets to separate the glass fragments by color, flint, amber, and green, while magnetic separators extract any residual metallic components from the caps or labels. The sorted cullet is then washed and pulverized into a consistent granular form. This material is a high-value technical commodity for the glass manufacturer, as it requires significantly less thermal energy to melt than the original mineral precursors of sand, soda, and lime. The cullet is transported back to the glassworks, where it is weighed and blended with fresh raw materials in the batching plant, exactly as described in the first chapter of this history. The silicate molecules that once formed a bottle in the hand of a consumer are now returned to the intense heat of the furnace, where they will be vitrified once again at temperatures exceeding 1,500 degrees Celsius. This circularity represents the ultimate industrial logic of the glass manufacturing process. The matter is never truly consumed, it is merely transformed through the application of thermodynamic and mechanical force. The journey of the glass is a perpetual loop, a continuous transition from a molten liquid to a solidified form, through the rigors of transit and consumption, and back into the incandescent core of the furnace. The facility remains in a state of constant, unvarying motion, with the sound of the conveyors, the roar of the burners, and the rhythmic clicking of the machinery forming a permanent acoustic backdrop to this evolution of matter. As the sun sets over the industrial landscape, the glassworks continue to operate. The silos remain full, the furnace remains incandescent, and the line of bottles continues to march with a disciplined mechanical regularity. Every unit that is produced is a masterpiece of consistency, a testament to the complex technical sequences that govern the modern world. The story of the standard glass bottle is a story of stability in a world of change, a journey of silicon and oxygen through the fires of technology and the requirements of commerce. The steady hum of the facility is the pulse of this process, a sound that signifies the ongoing, relentless transformation of the Earth's minerals into the functional objects of our lives. The technical history of the glass bottle concludes here at the threshold of its next incarnation. The container that was once a river of molten silicate is now a collection of fragments ready to be melted and formed once more. The logic of the process is complete, the circle has been closed, and the movement of the glass continues, without beginning and without end, in the silent rhythmic service of global industry.